in a big, big circle around this. Those are the x's with big magnitude. So this is magnitude of x much bigger than 0. And now it's a circle because it could have any argument, it could have any angle. I know that x to the n will be even bigger. I'm going to shrink the scale on this red plane so that I don't have to draw it off the table, but it'll go to some huge circle. Now, what will happen when I take x and I take a walk with x? I think of it as a dog on a leash, and I lead it around this circle. So we know what happens. The magnitude, remember I'm pretending that this polynomial is x to the n because it's like x to the n. The magnitude will stay the magnitude of x to the n, the same thing it was before. So it'll walk around this circle. And the real polynomial will stay close to this circle. It'll sort of dance around like a dog would on a leash after all. Something else is happening though. As I move x around, this one moves n times as fast because I'm multiplying the angles by n. So it actually goes around n times. For the purposes of this proof, it's enough to know that it just goes around. But we'll see why the n is important there too. So as I move around here once, I move around the circle actually many times. Okay, that was nice, but did it help? Not obvious. Now comes the trick. Here's the rest of the proof. Once you see this, you just know it's right. I'm going to shrink the blue circle down to the point 0, little by little. And I'm going to watch what happens on the right-hand side. On the right-hand side, this circle, and remember the real values of the function were dancing around this circle somehow, but they're a nice continuous curve that meets up to itself again. This circle will begin to shrink too, because I know that when x is 0 or very small, this circle has to be very close to C. So somehow the circle shrinks down in all directions in some very uneven way, but at the end of the day, it forms a little circle around and see if x is performing a little circle around 0. Now, in that process, somewhere, this circle has to pass through the origin, and that's where I catch my root. So somewhere along the line, as it shrinks, I have to see a picture like that. And that's the point which I was looking for. That point happened maybe from over here, and it will be a point on a smaller circle here where this function actually goes to 0, where it has 0 value. We said that it really goes around n times. So actually, this path is going around n times, and as I shrink, it'll keep going around n times. So there'll be n of these curves that move through the point one at a time, or maybe all at once. And so there'll be actually n roots. And so that's the full fundamental theorem of algebra.
If you're still watching this video, you've got the sort of attention span that makes me think you might enjoy the Hello Internet podcast, which features fellow YouTuber CGP Grey and myself. We talk about all sorts of things. Very often we talk about what it's like making YouTube videos. If you'd like to find out more, check out the links. I'll put things in the video description.
With their sandwiches, help yourself to sandwiches, please.
Oh, how nice. Thank you.
So,
Oh, you mean like right now? Or just
yeah,
whenever?
go ahead.
Oh, okay. I just...
Dream Corp LLC.
okay, let's begin. My name's Randy Blank. Welcome to Dream Corp LLC. Now, on the questionnaire, one of the questions is, have you wet the bed while in a dream? We all did it probably as children, and I will be the first to tell you, I have you all beat. I wet my bed every single night. It's like putting a gel.
Can I ask you a question, Brady? What is the most difficult way to earn $1 million?
Making YouTube videos.
Well, you probably know much more about that than I do. One of the most difficult ones is to solve one of the millennium problems in mathematics, which were set by the Clay Mathematical Institute in the year 2000. One of these problems is called the Riemann hypothesis, and it refers to a work of a German mathematician, Bernhard Riemann, which he did in the year 1859. So this is just one of the problems. In fact, there are 7, and only one of them has been solved so far. And interestingly enough, the person who solved the problem has been fined the $1 million. So it just shows that mathematicians work on these problems not because they want to make some money. I think it is now the most famous problem in mathematics. It took the place of Fermat's last theorem, which was solved by Andrew Wiles and Richard Taylor in the mid-1990s.
But that wasn't a millennium problem.
That was not a millennium problem. The most essential thing here is what we call the Riemann zeta function. And the Riemann zeta function is a function, so a function is a rule which assigns to every value a certain number. A Riemann zeta function, it assigns a certain number to any value of s, and that number is given by the following series. 1 divided by 1 to the power s plus 1 divided by 2 to the power s plus 1 divided by 3 to the power s, 4 to the s, and so on. So, for example, if we set s equals 2, zeta of 2 is going to be 1 divided by 1 squared plus 1 divided by 2 squared plus 1 divided by 3 squared plus 1 divided by 4 squared, and so on. So, what is this? This is 1. This is 1 over 4. This is 1 over 9. This is 1 over 16. So this is an example of what mathematicians call a convergent series, which means that if you sum up the first n terms, you will get an answer which will get closer and closer to some number. And that number to which it approximates is called the limit. But the limit here is actually very interesting. And it has been a famous problem in mathematics to find that limit. It's called the Basel problem, named after the city of Basel in Switzerland. And this Basel problem was solved by a great mathematician, Leonhard Euler. And the answer is very surprising. what earlier showed is that this sums up to pi squared over 6. And so you may be wondering, what does this sum have to do with the circle? Why would pi squared show up? But Euler came up with a beautiful proof. I'm not going to explain it now, but it's something which you can easily find online. This series is just one example of this Riemann zeta function, but you can try to do the same for any other value of s. So for example, if you take s equals 3, you will get the reciprocals of all the cubes, and you sum them up, and so on. So this will again be a convergent series, and you can wonder what the answer is. That would be zeta of 3. You can also try to substitute negative numbers. And this is very interesting because if you just substitute s equals negative 1, then what are we going to get? So you will get 1 divided by 1 to the 1 to the negative 1 plus 1 to the 2 to the negative 1 plus 1 to the 1 over 3 to the negative 1. If you take the reciprocal of something which is the inverse of something, then you will get that thing. So this will be 1. This will be 2. This will be 3. This will be 4. Does it look familiar?
Yes, I have seen that before.
We have arrived at the famous sum of all natural numbers, 1 plus 2 plus 3 plus 4. But you see, now we obtain it in the context of the zeta function. So this is what we call a divergent series. There is no obvious way how we could possibly assign a finite value to it. This sum is infinite. It does not converge to any finite value. But this context, if we put this value, this infinite sum, in the context of this function, there is actually a way to assign a value to this to s equals negative 1. And this is what Riemann explained in his paper. And so what Riemann said is that actually we should allow s to be not just a natural number, like for example 2 or 3 or 4, when the series is converging, but we should allow also all possible real numbers. And not only real numbers, but also complex numbers. The way you get complex numbers is by realizing that within real numbers, you cannot find a square root of negative 1. So what to do? One way is to ban square root of negative 1 and say, this doesn't exist, we cannot use it. But in mathematics, we have understood a long time ago that actually there's a much better way to treat this square root of negative 1. We can simply adjoin it to the real numbers. Think of real numbers as points on a line. Here is 0, and here is 1, and here is 2, and then you can mark your favorite fractions. For example, 1/2 is exactly the middle way between 0 and 1, and say 1 and 1/3 would be sort of a third of the way between 1 and 2. But then you also have things like square root of 2, for example, somewhere here, and then there is pi, which is just to the right of 3. So all real numbers live here. Square root of negative 1 cannot be found anywhere on this line. But we don't give up. We say, you know what? Let's actually draw a plane. Let's draw another coordinate system. And let's mark square root of negative 1 on this new coordinate axis. You see, if we do that, then every point on this plane becomes a number. So that would be 2 times square root of negative 1. Then if I take 3 times. But more than that, let me find a number which is on the intersection of this line. I can draw a vertical line which goes from 2, and I can also draw a horizontal line. There is this point of intersection. So this point also will represent a number, which will be 2 plus 3 times square root of negative 1. So in other words, a general number is going to have what we call a real part. That's the projection onto this axis, and the imaginary part. That's the projection on the vertical one. The rotation is a little bit clumsy. Instead of square root of negative 1, they write I. So then, for example, instead of writing 2 plus 3 square root of negative 1, we'll just write 2 plus 3i. It's an imaginary number. We imagine it. We cannot find it on this real line. So we have imagined it, and then we have adjoined it in our imagination. Real numbers comprise all points on the real line on this axis, and complex numbers comprise all the points on this brown paper. If you could extend the brown paper all the way to infinity, right? So let's go back to Riemann. What Riemann's insight was, is he said, look, let's think of this argument of the zeta function, this number s. Initially, we thought that s could be 2, 3, 4, and so on. But then we realized that actually any real number to the right of number 1, not including number 1, because actually in this case you cannot assign a value. It's a divergent series and it goes to infinity. But anything to the right, and I'm marking it with red, for all of them, this function is actually well defined. So, but then he said, we can actually do more. We can think of S as being a complex number. So instead of thinking of S as just being a point on this line, we can take S anywhere. It will be convergent if it is to the right of this line. So you see, this is the line which sort of, to the right of this line, live all the complex numbers whose real part is greater than 1. So it turns out, and it's very easy to show, that anywhere in the shaded area, except for this line, so to the right of this line, for any value of S in this area, this function is converges to something.
So if I put 6 plus 9i into the Riemann zeta function, I'll get convergence.
That's right. You'll get a convergent series. It will converge to something, which is not going to be a real number. It's going to be a complex number because you're going to add up infinitely many complex numbers. But there will be a certain number to which will be closer and closer approximated as you go along, summing up this series.
So far, basically everything to the right of this line
It gives us a bona fide value.
will come out to play.
Will come out to play. It will give us a bona fide value.
Can the imaginary part go negative?
Yeah, but the imaginary part, yes, the imaginary part is okay. Can be negative or positive, but the real part has to be greater than 1. But now you are in the context of a theory of functions with complex argument. And it is what we call a holomorphic function. So it has some very special, very nice properties. So one of the properties that this kind of what we call holomorphic functions enjoy is what we call analytic continuation. So we can extend the definition, the domain of definition of the function. There are methods which enable us to kind of push the boundary and go and expand the domain in which the function is defined. And in his seminal paper, Riemann did precisely that. He explained how to extend this function to all possible values, except for 1. So there's only one value where there is nothing you can do, that somehow it will be undefined. And we call this a pole or a singularity. And what is that value? That value is actually s equals 1. So this is a bad point in some sense. This is a point where we cannot extend.
So, and there's 0 I component. There's no imaginary.
That's right. So this is a point which is actually a real number. So it's funny because you would think that 1 is in some sense better than I. But at I, this function will be perfectly well defined. But at 1, it will not be well defined. It will have a singularity. But luckily, it's the only singularity. So what it means in particular is that there is a way to assign a value to -1. In other words, there is a value zeta of -1, where by zeta we now mean this extended function analytically continued to the whole complex plane, and that value will be, you guessed it, -1/12. It is in this sense that people say you could regularize the sum 1 + 2 + 3 + 4 and assign to it the value -1/12 because it shows up as the value of the zeta function where naively you are supposed to get 1 + 2 + 3 + 4. But now you are getting this value by a much more sophisticated procedure, by starting with a function of a complex argument and extending it beyond the initial domain of definition.
So no matter what number I pluck from here or here or here or here or here and feed it into the function, I'll get a number of some sort.
You will get a well-defined number, uniquely defined number, and you can calculate it on a computer because this number can be represented by some integral, for example. There is an explicit formula for it. Okay, so you will calculate, I will calculate, we'll get the same result. There is no ambiguity. The only point where it's not well defined is the point s equals 1.
This is like the Achilles heel or the
It's an Achilles heel. That's a very good way to put it. It's an Achilles heel of that function. And it's very important. It's responsible for a lot of things that's happening to it. So it's a very important point. So Riemann hypothesis is the following. It's about the zeros of this zeta function. In other words, it's a question about for what values, for which s we have zeta of s equals 0. That is a $1 million question. For which values of s do we have does this function equal 0? And so Riemann, here there is one point that one has to make, which is that there are some sort of obvious zeros. So it just so happens that the value at -2, for example, is equal to 0. The -4 is equal to 0. So So, in other words, all the even negative numbers, for some reason, it just so happens, and you can see it, for example, from the functional equation, that the value is just going to be 0. So there are some obvious zeros, so to speak, which we already know. The question is, what else? Where else are where are the other zeros? And it's actually very easy to see that all other zeros have to be concentrated in this one strip. So on one side of the strip is the vertical line, is the vertical axis, and on the other side of the strip is this line, when real part is 1. And so so this is called the critical strip. These are all the complex numbers for which the real part is between 0 and 1. And so inside this critical strip, there is a middle line for which the real value is 1/2. And we look at all the numbers for which this is the real part. For example, 1/2 plus 5i will be a point somewhere here, so it will be on this line. And what Riemann suggested, the number of zeros is the minimal possible. They all concentrate along this critical line, according to Riemann hypothesis, which still hasn't been proved.
His hypothesis is that all the zeros to his function lie on that line, except for these ones.
Exactly.
All the zeros lie on that line.
On that vertical line, which goes through the point 1/2. That is exactly the statement of Riemann hypothesis.
So one way to disprove the hypothesis would be to find a zero somewhere in that blue shaded
Exactly.
area.
We know that all of them are going to be in the blue shaded area. The question is whether they are on this one specific line. And believe me, a lot of people have been looking for a counterexample, which, by the way, one wins $1 million if one proves Riemann hypothesis or disproves it. So if somebody could find a point in here, which is a zero but is not on this line, will also win $1 million. So a lot of people have been searching but haven't been able to find.
Have a lot of zeros been found on the line?
Yes, a huge number. I don't remember, but I think trillions of numbers. So all the zeros that have been found are on this line, and there's constantly search going on for more and more. The way I explained it, it sounds like an esoteric problem. But actually, in this case, there is more to this than meets the eye. Because Riemann, in that amazing paper that he wrote in 1859, he also explained that this behavior of his zeta function, which is now called after him, the Riemann zeta function, and more specifically, the behavior and location of the zeros of that function, has a direct bearing on the distribution of prime numbers. And prime numbers are incredibly important. So prime numbers are, something that people have been studying for millennia, right? So Riemann was able to connect the properties of this function to the distribution of prime numbers. And he obtained a beautiful formula which tells you how many prime numbers there are, say between 1 and 100, between 1 and 1,000, between 1 and 1 million, for any n, between 1 and n, using his zeta function, which is absolutely astonishing. Because if you think about zeta function, something has to do with complex numbers and with analytic integration and so on and so forth. So it's a particular branch of mathematics which is called complex analysis. But prime numbers live in a different branch of mathematics, in number theory. And it is a big surprise that actually the two things are very closely connected. But this relation that Riemann found is predicated on the Riemann hypothesis. It's predicated on knowing that all the zeros are located on this critical line. That's why this Riemann hypothesis is so important, because it is only if we know that Riemann hypothesis holds that we can obtain all these deep results about distribution of prime numbers. We replace this series by the sort of regularized values. And I really like to think of these regularized values as sort of like, removing imagine like a piece of gold which is surrounded by this infinite amount of dirt. And you kind of throw away this dirt and you're left with this little piece of gold. So what I'm trying to say is that
With Wix, you can create a professional website that looks stunning. Just go to Wix.com. The best part is you can update it and keep it fresh whenever you want. I like changing up the background. It instantly gives my site a whole...
Well, the usual way that people discuss it is to talk about perfect squares first. So if you have studied the Pythagorean theorem, there's a formula that the square of the hypotenuse is the sum of the two squares of the sides of a right triangle. So you might ask, if the sides of a right triangle are whole numbers, might it happen that the hypotenuse is also a whole number? They're called Pythagorean triples, and the Greeks figured out all of the Pythagorean triples. Okay, so what happened next is, I think it must have been very natural to look at the equation a cubed plus b cubed c cubed, and a to the fourth plus b to the fourth equals c to the fourth, and so on. So this is now in the realm of algebra, and you can plug in values for a and b, and you'll see that these equations, infinite number of equations, seem not to have solutions. Well, so the story is that Fermat was reading the text of Diophantus, who is the Greek mathematician best known for this type of problem, and in the margin of his copy of Diophantus, he wrote some marginal notes so that I can prove that for higher exponents, bigger than 2, there are no positive integer solutions. And then famously he said, but my solution is too long to write in this margin. And in his copy of Diophantus, which was inherited by Fermat's son Samuel de Fermat, there are many, many marginal notes. And Samuel published a revised version, an annotated version of Diophantus's book, in which all of his father's writings are reproduced. And the reason that Fermat's last theorem is called Fermat's last theorem is that all of the previously examined marginal notes proved to be correct, or at least they were proved to be correct or incorrect, mostly correct, by mathematicians after the 17th century. And there was this only one assertion that remained. It was the last one on his hit list. And, you know, again, I'm not an expert in the history of mathematics, but I think most people are convinced that when Fermat was a mature mathematician, he realized he did have no proof of this thing that he wrote in the marginal note. And in fact, later in his life, he devoted a lot of attention to special cases of that type of equation. It's not just the cubes, but it's the cubes and the fourth powers and the fifth powers and so on. And Fermat himself, later in his life, took care of the fourth powers. Well, the cube certainly must have bothered him, because he, after all, he knew about squares and he knew about fourth powers, and cubes were right in the middle.
The theorem is that there is no solution. There's no whole number solution.
That's right.
Yeah. Would it have been, or would it have been more exciting or more attractive to a mathematician to prove him wrong and to find these three numbers that you could plug in that would do it? Would that have been more triumphant?
Well, it would have been very exciting. It would have made lots of news, and then the proof, so to speak, would have been simply a single counterexample that would have fit, very neatly in the newspaper column, and there would have been some story, mathematician in Australia finds the first counterexample to Fermat's last theorem. Certainly was big news either way. The main thing about Fermat's last theorem is that over the centuries it gave rise to a tremendous amount of new and fruitful mathematics. That people really developed new techniques to try to solve that equation that proved to be, infinitely versatile.
So a bit like going to the moon let them develop lots of other technologies along the way. This was the going to the moon of mathematics.
That's a fine analogy. I mean, when you formulate a problem in mathematics, no one knows whether this problem will really be helpful for mathematics as a general enterprise. And, for whatever reason, Fermat's equation has led to a tremendous amount of new mathematics. So when I was a graduate student, we're talking, roughly 40 years ago or 45 years ago, Fermat's last theorem was kind of some curiosity. Everybody knew about the problem, but no one really had any approach to it. And there was no kind of fundamental reason why the problem was going to have a positive solution. And when I was a student, there was a tremendous interest in what are called elliptic curves. And it was realized around 1968, 1969, 1970 by André Weil and Goro Shimura in Princeton, who built on the work of Yutaka Taniyama, who was his buddy in Tokyo in the 1950s. Taniyama had passed away. And there was this gradual understanding that elliptic curves really were related to modular forms. And again, that was some completely, apparently inaccessible, outstanding conjecture, and it was thought to be an incredibly hard conjecture. And then in the early 1980s, a mathematician came around, and I say that literally because he was sitting here in this office. His name is Gerhard Frey. At the time, he was at the University of the Saarlands in Saarbrücken. And he came. Well, I didn't know it either. And he came around and he had this scheme for relating Fermat's last theorem and the modularity conjecture. Somehow he realized for the first time that if he had a solution to Fermat's equation, this would give him an elliptic curve which apparently could never be modular. I was really skeptical because I knew that some of the things that he said that he needed in his argument were very hard. Well, for me, a really important thing was in 1985, Jean-Pierre Serre, who's one of my mathematical heroes in Paris, sat down and kind of tried to distill everything that had been said about Frey's idea. He came out with a very clear letter, and this letter basically said, if you can prove this tiny little result, which he called epsilon, because the number in calculus, epsilon is a small number. He said, if you can prove this tiny little epsilon, then you can really show that the modularity conjecture, which he called V at the time, implies Fermat's last theorem. So epsilon became, for me, a holy grail because not only was it something fairly well encapsulated and very clear, and this was the kind of thing that I'd thought about before without success, but nonetheless, while thinking about yet another problem, it occurred to me that I really had some new information that I could possibly bring to bear on this epsilon. What I first did was say to myself, what's the simplest possible case where I can think about this? What's the simplest possible prediction? I tried to settle that. I said, well, if you have to start somewhere, I know about this simplest case, so I had this thing in my mind, and I thought about it off and on during the academic year, 1985-86. And during this year, I was teaching calculus. I was busy with things. Colleagues come in, they want you to be on committees. And finally, my final grades were submitted in May 1986. And I started thinking about this problem again. First, I was on the East Coast for a while, going to Europe, and then I found myself in Paris. Finally, I found myself at an empty desk at the Max Planck Institute in Bonn, where I could just sit and think. I thought about this yet again.
You can sit at the desk with your head in your hands and think. I mean, if I was a fly on the wall when you were trying to crack this problem, what would I have seen? What's it look like?
Well, it's probably, I probably had a pad of paper in front of me and a pencil or a pen. We didn't really have computers quite yet, although they were starting to come. And when you visit some institute, you don't have all your stuff with you. You don't have lots of books. You don't have all your paraphernalia. So I was really just kind of sitting there, and I started writing, and if you look in my office, you'll find lots of old pads where I sit and write, and the page might start, what do we know? What are we trying to do? Let's summarize the situation so far. Let's try this. And to my astonishment, I was finally able to crack that problem, the simplest case of epsilon.
So inspiration comes at preordained times. Like you sit down and say, okay, for the next 2 hours before I meet my friend Bob for a hot dog, I'm going to have an inspiration and try and solve the problem. And that's when it happens. It doesn't happen at odd times when you're lying in bed.
Oh, it can. I mean, if you think about something very intensively, then you just carry it around with you. And, lots of my colleagues say that while they're swimming, they had some insight. Or, lots of people say in the middle of the night, they jumped up and they said, my God, why don't I try the minus sign instead of the plus sign? And this can indeed happen,
Not for you, though. You're at the desk kind of guy.
I think in this particular situation, I was at the desk. I knew for the first time that I could do something that I hadn't done before, that no one had done before. This was a special case of this so-called epsilon. And I kind of wrote it and rewrote it to make sure I was really right. finally, using the very first Macintosh that I had access to, I typed out a letter to Barry Mazur at Harvard, and I sent him this letter explaining what I'd done. And then I spent weeks and weeks trying to do the general case. I couldn't see what to do. And then, fortunately, there was an international Congress of mathematicians that occurred once every 4 years on the campus of UC Berkeley. So I was right here. I came back in August for this international Congress, and Barry Mazur was there. And I spoke to him, and I said, Barry, I sent you this letter explaining how I did a special case, and I really wonder, what I have to do now to do the general case. And he looked at me completely quizzically. He said, well, but you've already done the general case. And basically, he, when he read my letter, it just seemed obvious to him that there was this extra little thing you carry along as a supplemental object, and this extra thing would just do the bookkeeping. And so we sat down at this Cafe Strada, which is at the corner of the Berkeley campus, and we had a cappuccino, and he kind of said, well, you just carry this around with you. And I was astonished. It was like this amazing moment where all of a sudden I realized that, in principle at least, there was no obstacle to proving this epsilon conjecture. I mean, it's like, my God, it's some special thing. An angel comes down and a light shines from the heavens or something. So this was really quite a thing. And since all of my colleagues were walking around the campus in this big international congress, I kind of told, a number of them that I had done this thing. Of course, in the beginning I was cautious. I said, well, I think I've done this thing. But people kept running up to me and they said, well, is it really true you've done epsilon? I lived in a world, and think I still do, where my colleagues are very generous with attributions and praise, and there isn't too much of this kind of race to be the first to publish. And people basically, I had little fear that someone would try to scoop me. On the other hand, what was a little worrisome was that I hadn't written down all the details. So I kind of had written down very closely the special case, but I hadn't kind of worried about writing anything more generally. So what happened was that during the year following that, 1986-87, there was a special program on algebraic geometry and arithmetic geometry at the Mathematical Sciences Research Institute in Berkeley, the MSRI. So I was up there with my colleagues, and I gave lectures every week. I gave another lecture. I was kind of giving like a mini course on my proof. And when I wasn't lecturing, I was furiously typing into the computer to try to expand and revise my manuscript. And kind of more and more details got put in, and there were certainly people in the audience who were appropriately skeptical. They asked me hard questions, and I didn't always know the answer to the hard questions. Well, how do we really know that this thing is in such and such way? And I would say, well, this was proved in the 1960s by Grothendieck, but it isn't quite written down in the place you expect, and then I'd have to go find an argument. Well, epsilon was not small. It was clearly a misnomer, and let me just get up and pull off a reprint. Here's my article. It was published in 1990, which really makes a lot of time between 1986 and 1990.
How many pages?
So it went through.
It's like a book.
Well, it's more than a pamphlet. If you open up this paper, on the very first or second page, there's Fermat's equation and an elliptic curve, but then they disappear. If you look at the actual article, it's more about the technicalities of the subject. It was a big deal in mathematics. It got write-ups in the press, including Science Magazine, if I'm not mistaken. Whenever there's a serious announcement of a major theorem, that gets a lot of attention, and people stop what they're doing to try to see what the basis of the proof is.
Who calls it Ribot's theorem? Obviously you don't get to make that name up. That just sort of evolves like it whenever a mathematician does this.
Well, yeah, that's right. So there's a general aversion to naming things after yourself. And very often people will give lectures and they'll say such and such theorem, and then in parentheses they'll write the name of the person who proves it, and if it's a theorem that they prove themselves, typically they write the first initial of their last name or something like that, or else they don't add any attribution, and the listeners understand, well, this is the theorem that the person is providing in this lecture.
You've done this thing which is important. You've built a bridge between two things which neither of which are on solid ground yet, though.
Well, that's right. So what I showed was that this modularity conjecture, which was thought to be, was felt to be true, but wasn't expected to be provable. I showed that thing actually implies Fermat's last theorem. I think the main takeaway from my theorem was that since the Weil conjecture, or Shimura-Taniyama, was likely to be true, that now you should think that Fermat's last theorem is likely to be true. For example, it probably wouldn't have been a really good idea to spend a lot of computing power looking for a counterexample of Fermat's last theorem.
Where was Andrew Wiles? He was in the room?
Well, that was the whole thing. So Andrew Wiles, of course he came around a few times, I guess, but basically he was holed up in his attic. And I didn't know that, and I think most people didn't know that. So he was, it's his statement that he was certainly intrigued by Fermat's last theorem as a child, and that as soon as he heard about this bridge, he decided to try to prove the modularity theorem because of its relation to Fermat's last theorem.
So is it sort of the situation that Andrew Wiles wanted to prove Fermat's last theorem by any means possible, and you'd given him a new means?
That's what he says. I mean, this is surprising to me because the modularity theorem by itself is a tremendous prize. And, it seems kind of strange that you needed the motivation of Fermat to go and try to prove it if you thought that there was some way.
That's not strange to me.
Well, anyway, that's what he says.
But yeah.
And we were all together, kind of lots of people in the subject, in a conference in Cambridge, England, in June 1993. And usually you go to a conference and you see the list of speakers, and each speaker has an hour. And the thing had been set up so that Andrew Wiles had 3 hours. So he asked the organizers, he said, I have something I want to discuss, and it will take me 3 hours, and I'd like those slots. They said, okay. And then in the first lecture, you could see he was proving, he was starting to prove the modularity of some class of elliptic curve. But the class of elliptic curves, at least in the first lecture, had no intersection with the class that you needed for Fermat's last theorem. But then the second lecture got a lot closer, and it became more and more apparent to people at the conference that in the third lecture, he was going to be able to do enough to get Fermat's last theorem. The crowd was growing, so a lot of the mathematicians, brought their colleagues who happened to be in Cambridge, and some of their family members, and I think there was little doubt that he would announce a proof of Fermat's last theorem, so I came and I sat in the front row center and brought my camera and snapped a picture of it. That was another moment when, this kind of time stopped, when I first realized what was going to happen. And then, when it actually did happen, there was this frenzy of activity. I mean, the director of the Isaac Newton Institute, where these lectures were held, had ordered a case of Napa Valley Brut champagne for the end of the lecture, and after the lecture we came out into the champagne for the end of the lecture, and after the lecture we came out into the common area, and the Isaac Newton Institute, where these lectures were held, had ordered a case of Napa Valley Brut champagne for the end of the lecture, and after the lecture we came out into the common area, and all these champagne flutes were produced, and these bottles started popping, and it was kind of really an amazing thing.
Between the time when you built your bridge and you published your paper and this lecture, did Andrew Wiles ever call you or write to you and ask for your help? Or
Not a word. Not a word.
You had no idea?
I had no idea what he was doing.
You knew who he was, though. He wasn't like a nobody.
Oh, absolutely. He was a friend and a colleague. I first met him when he was a graduate student in Cambridge. And in fact, when I first came to Berkeley, the first year that I was here, he was one of the first people that I invited. He came and spent a week and gave a lecture or two.
Do you like that? Do you like that he kept it a secret? Does that make it like a nice surprise party? Or to this day you feel baffled by it? I mean, you seem a lot more collegiate. You're telling me when you solved your thing, you were running around telling everyone, and he's quite secretive.
Well, it's very unusual behavior. And, you know, you can say in retrospect that it was really justified because he was afraid that people would kind of jump all over it because of the importance of the modularity conjecture and Fermat's last theorem. But he did not tell me what he was doing. He did confide in two of his colleagues at Princeton as he was giving his graduate course where he was working out the ideas that were instrumental in his paper. I think it was only a few days later that I got a copy of this manuscript. And the manuscript was very thick, you know, it was like 300 pages, single spaced, you know, typeset by TECH, mathematics typesetting program, and we were supposed to be the kind of referees looking at different parts of the paper, and I was assigned to a part that turned out to be problem-free. And Nick Katz looked at a part that turned out to have problems, a problem.
Was that shattering for you, or do you like that? Does it make you think, this is good, you know, I like the rigor, this is how mathematics works, or is it really deflating after the high of the champagne?
You mean finding the problem? Well, one of the aspects of the whole thing is that I had gone out pretty far on a limb telling everybody that Andrew Wiles had proved this thing. And the way that started was that when the New York Times first heard about his announcement, they asked to speak to him, and Andrew turned to me and said, Ken, you know, you speak Gina Pilato. So I went upstairs and spoke to her for a very long time, explaining the whole thing. And then somehow the media kept calling me because it was understood that somehow I was his designated spokesperson. So I spent that entire summer lecturing about his theorem and fielding phone calls from the press.
How long after the Wiles announcement did Katz time?
Oh, I think it was like 2 weeks. What happens in mathematics is if you have a proof that seems to really be, seems to have a lot of internal logic to it, and there's something that's wrong with the proof, your immediate reaction is to say, well, you know, this is just some technical problem that I need to fix. And I think that Andrew Wiles, when he found out about the gap, expected that he would be able to repair it in short order. So it really took a while before there was realization on his part that this was a serious problem that couldn't be fixed immediately just by the tools in front of him.
If you were the person who was taking all the calls from the press, for whatever reason, did that mean you were contacting Andrew Wiles a lot and saying, can you give me an update? Because I'm getting all these calls, mate, and I don't know what to tell them. Like, were you calling him for updates so you knew what to say, or had he gone to ground?
Not especially. He kind of went dark. He was working on mathematics, and I wasn't getting a lot of information out of him at that time. You know, it was all poised in the balance, right? And, wasn't clear whether or not this would get repaired or not. And then, you know, wonderfully, it turned out that there was this repair to the proof, really some completely new insight, actually, by Andrew Wiles and Richard Taylor, who worked together over the summer, and this was the summer of 1994. And they had a preprint out in the fall of 1994, where they explained their new method, which is now called the Taylor-Wiles method. And that really circumvented a lot of the more complicated arguments in the original preprint. And the two articles were published together the following summer, which is the summer of 1995, in the Annals of Mathematics. It was a relief, but it was not a joyous relief. You know, and Richard Taylor came to me one day, again at MSRI, where I happened to be, in fall of 1994, and he said, we have some good news for you. And then the next day he handed me a copy of his paper. So So that was kind of very good. And, you know, I don't remember there being a huge celebration on the moment of the release of that reprint, but it just kind of gradually built. People understood that the proof was complete. And then there was a very large instructional conference at Boston University in the summer of 1995. Different people got up and explained the different elements of the proof. Well, it was a fabulous piece of mathematics. As impressed by what I did, and impressed as I am by my own work, I'm even much more impressed by what they did. They had some really new insight, and this insight has percolated through our whole subject for the last 20 years. One way to say what they did is they showed that somehow modularity is contagious, in the sense that if you have something that has a little piece of it being modular, you can parlay that into the modularity of a full object. First of all, Wiles was obviously intensely driven to do this. He was really motivated, and he said, you know, I'm going to do this one way or another. And he brought in all sorts of different techniques that hadn't been related to the problem before. What's amazing, for example, there's a whole subject in algebraic geometry called deformation theory that was going on when I was a graduate student that I didn't learn. I thought that was really far removed from anything involving elliptic curves. And in the years before Wiles' announcement, Barry Mazur had developed this new technique of deformation theory in Galois representations, and it turned out to be exactly what Wiles needed, the language and the techniques that he needed for this discussion. And so, you know, something that seemed to be far away technically turned out to be crucial. Well, I think, you know, just informally, everyone understood that the proof of Fermat's not theorem. But in fact, when you looked at the article, just like my article, there was something internal to the theory of modular forms and Galois representations. And Wiles' article and my article share the trait that Fermat's equation occurs exactly once in the article in the beginning, and then you get down to the real stuff. I'm very happy with the recognition that I've gotten, and I'm very proud of what I did. And when students come into my classes, they know about my role in Fermat's last theorem. A lot of them have seen the video that was broadcast on Nova and BBC. And I think, you know, if you do something very, 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 very famous, then you have an encore problem where people say, you know, what great thing are you going to do next? And try to be more or less a normal guy and not just on the shoulder.
Desperate to rediscover what Fermat's proof might have been.
Is it widely held that he had done it, or had he just claimed? Like, was he telling the truth?
I think by the time we get to the 20th century, it's quite clear that this is an incredibly complex problem.
When I was about 10 years old, I found a book in the public library which talked about this problem. And like many other mathematicians, that's one of the things that got me excited about mathematics. Obviously, as a 10-year-old, I didn't do very much on this problem. I kept trying in my teenage years, and then I abandoned it when I was a student. This problem has a long history. It was tried by many mathematicians in the 19th century, but most mathematicians seem to have given up in the 20th century. Until about 8 years ago, there was a big breakthrough, and someone related Fermat's last theorem, this is the problem I've been working on, with another well-known problem in number theory. And from that moment, when that link was made, I've worked on it. So it's about 7 years now. I didn't start with any idea on how to solve this problem, so that was a problem, and it took me 5 years to get the first real breakthrough, and then I finished it probably about 3 or 4 weeks ago. There are lots more problems in mathematics. There are many unsolved problems. I think I'll wait until I've written this solution in a way that satisfies all the experts, and then I'll start thinking about my next project. The main significance of this problem is symbolic. One doesn't expect any real application of this kind of result, but one never knows. Primarily, it's symbolic because so many mathematicians have tried it. It's led to the creation of so much mathematics itself. Everyone has thought of it as the dream of mathematics to solve such a problem.
Welcome to tonight's special program on Fermat's last theorem. And I see a few seats and a few people coming in, so please feel free to take a seat while I make a couple of introductory remarks. I'm Will Hurst, the publisher of the San Francisco Examiner, and I'm going to be the moderator for tonight's session and introduce some of the speakers. On June 23rd of 1993, something extremely exciting in the mathematical world happened. Some of us were reading the New York Times innocently that day. Others heard about it via email or maybe a day later. And that was the announcement that a mathematician named Andrew Wiles had proved something that mathematicians had been trying to prove for 350 years. He had finally resolved Fermat's last theorem in the affirmative. Now, tonight's presentation is really aimed for a general audience. And so we expect that we may have some students in the audience, professionals from other allied fields, perhaps some professional mathematicians as well, and members of the general public that are interested to find out why the fuss about this theorem, what's exciting, how did Andrew Wiles do it, what does it mean, and we're going to try and get at some of those questions, and we have some very talented and brilliant speakers who have condensed a lot of complicated mathematics into some simple talks of about 10 minutes each. I don't think anybody should be worried if they miss a detail here or there. Even professional mathematicians go to talks and miss a detail here and there. But try and get a hold of the general concepts, feel the flow of it, and we're going to have some questions at the end, and don't worry, there will not be a quiz. Thanks ought to go to the Mathematical Sciences Research Institute, who is our primary host this evening. MSRI, as it's known, is a research institution, a little bit like the Princeton Institute for Advanced Study, located over in the Berkeley Hills. They have a Zen monastery-like building overlooking the Bay Area. And a lot of interesting people come through there, mathematical researchers who give talks, listen to other people's talks, and talk to each other. Bill Thurston, who is the director of MSRI, set out a goal for the institution to do some outreach. This was before the announcement of the proof of Fermat's last theorem, and so this program tonight is an effort to try and have MSRI be the agent for public awareness of mathematics, and we hope you'll enjoy the program. I guess I should also answer the question, why am I here? Why is Will Hurst here? And I can only offer two answers.